Okay, I'm going to work on a possible quiz question here. It's out of the Phillips Exeter Math 2. It's page 30, number 1. I had originally done this video live during a lecture in class, but the second part had gotten corrupted, so now I'm going to redo it, and hopefully it works this time. So what we're looking at is a three-dimensional coordinate plane with the points 5, -3, 6, the origin 0, 0, 0, and another point 3, 7, 1. And the idea here is to show that angle ABC is a right angle. Now I'm not going to take a whole lot of time to draw this in 3 dimensions. I'm going to take this idea and just show an idea of it in 2 dimensions. So what we have here is it's saying that B is a right angle. So I'm going to go ahead and draw a right angle here. And we have to show that that's a right angle, that's B. And then we'll have C over here and A up here. So our B is 0, 0, 0. Our C is 3, 7, 1. And our A here is 5, -3, 6. Now what I'm going to do here to show this is a right triangle is I'm going to use, first I'm going to find the side lengths if this were a triangle of ABC. Because if it is a triangle ABC, then what we can do is use Pythagorean theorem, check our side lengths in Pythagorean theorem, and it should check out to work, which means that A or B would be a right angle. So I'm going to use a distance formula in 3 dimensions here. So look over here, I have the distance from, I'm going to go from A to B. So I'm looking for this length right there. So that length right there, to find that length, I will do square root. Now the distance from 0 to 5 is 5. So square root 5 squared, plus the distance from 0 to -3 is 3, 3 squared, and the distance from 0 to 6 is 6, so I'm going to go 6 squared. So I have square root of 5 squared plus 3 squared plus 6 squared. Do some quick calculating here. Square root of 25 plus 9 plus 36. And we end up with square root of 70 for side AB. I can do the same thing for BC. So I have square root 0 to 3 is 3, 0 to 7 is 7, 0 to 1 is 1. Plug those into Pythagorean theorem. And now I would have square root of 9 plus 49 plus 1, which is square root 59. That would be BC here, root 59. And our last side, AC, a little bit more difficult because we're not starting at the origin, but our distance from 5 to 3 is 2, so I can do square root 2 squared. The distance from -3 to 7 is 10, so plus 10 squared. And the distance from 6 to 1 is 5, so plus 5 squared. That'd be the square root of 4 plus 100 plus 25, square root of 129. So AC would be root 129. Now hopefully we see a little pattern here of how we're going to show this, but if you're not seeing it, we're going to use, to double check this, we're going to use the converse of Pythagorean theorem. So a squared plus b squared equals c squared. So we're going to double check that root 70 squared plus root 59 squared equals root 129 squared. We can simplify by, I guess we'll call it canceling, but we have a square of a square root, so we get 70 plus 59, that equals 129, and that checks. Okay, now let's look at another way we could do this using vectors. This way is a little bit shorter, but definitely entails some ideas about vectors. So we can draw the same picture we did in the last problem where we used Pythagorean theorem. We have a vector that's going from, we'll say from B to C. So we're going from the origin to 3, 7, 1. And then we have a vector that's going from B to A. Now our vectors could go in the opposite directions. I just did it this way because it's easier to find vectors when you're starting at the origin than when you're starting from a random point. So now we have these two vectors going from B to A. So I'm going to write that here, vector BA. And we have to actually find the components of this vector, or what the vector is. So the vector is going from 0 to 5, so our x component is 5. It's going from 0 to -3, so it has a y component of -3. And it's going from 0 to 6, so we have a z component of 6. So again, that's why I started at B. We could have gone in the other direction, gone from A to B. This would have worked in the same way. If we went the other direction, then we'd be going from 5 to 0, so that would be a -5, because we're traveling from 5 to 0, which is a -5 direction. That makes things a little bit more complicated. That's why I chose to go from B to A. Okay, I'm going to go ahead and finish out this vector from A to B, just so we get that idea. So we want to find the y-coordinate going from -3 to 0. Well, it's going to go from -3 to 0, you'd have to go 3 in the y direction. And then to go from 6 to 0, you would go -6 in the z direction. So you notice that our vector just has opposite components. Same vector, which gives you the same magnitude, same length, and it's going in the opposite direction. Okay, so once you have that, now let's find the vector for BC. So vector BC, this one's the same as that BA. We're going from 0 to 3, x component 3, 0 to 7, y component 7, 0 to 1, z component 1. Okay, now the goal is to show if those vectors are perpendicular or form a right angle. So if I look at, say, vector BA and vector BC, and I want to show that they are perpendicular, we can use what's called the dot product. And what the dot product is what happens when you multiply the x components. So again, I'm looking at just BA here and BC. If I multiply the x components, I get 5 times 3. Okay, and I add that to what happens when I multiply the y components. Negative 3 times 7. I add that to what I get when I multiply the z components. 6 times 1. When I simplify this, I get 15 plus a negative 21 plus 6, which simplifies to 0. And that's what I'm looking for, because if your dot product of two vectors is 0, then that means that would have to be, those two vectors are perpendicular, or that would form a right angle.